The theory of electromagnetism is not only valid in free space and air, but it can be applied in a very similar fashion in materials. An important illustration of the importance of electric fields in materials is that of the metal oxide semiconductor field effect transistor, the MOSFET. Two schematics are shown here for a PMOS and an NMOS field effect transistor. P and N refer to the type of silicon semiconductor used. N refers to N-doped and P refers to P-doped. MOSFETs are crucial for modern computing and involve all three types of materials: semiconductor, insulator, and conductor. Here a silicon semiconductor substrate, either N-type or P-type, is separated from a conducting electrode, the gate electrode, by an insulating layer, often silicon oxide, which is shown here white. Charging the gate electrode either negatively, as on the left, or positively, as on the right, creates an electric field that penetrates through the insulator into the semiconductor substrate. The application of the field creates a conductive channel, or if the gate electrode is not charged and no field is present, the creation of such a conducting channel is inhibited. The channel is created because the majority charge carriers of the semiconductor substrate are pushed away from the surface. So in the case of an N substrate, the negative charge carriers are pushed downward, creating a positive channel at the top. The channel permits the free flow of charges from the source electrode to the drain electrode. Source and drain electrode are typically also silicon that is doped in the opposite way than the silicon substrate. In order to describe a MOS field effect transistor with electromagnetic theory, one needs to know how electric fields behave in materials and how electric fields change at boundaries of different materials. This simulation shows how an N MOSFET works. A positive voltage of 3 volts is applied to the gate electrode at the center. This electric field penetrates into the brown semiconductor and creates a conductive negative path for electrons to travel from the left source electrode, that is at 0 volts, to the right drain electrode, that is at a positive 1 volt potential. The two Maxwell equations of electrostatics, namely divergence of D equals the charge density and the curl of the electric field strength is 0 everywhere, apply equivalently in materials. There is one important difference though, and that is that the charge density only considers free charges, not charges that are due to polarization. Charges caused by polarization, bound charges, are not free and cannot create an electric flux density. This distinction is not necessary in free space, since free space cannot be polarized. Generally, the electrostatic field therefore does not behave any differently in media, as long as those media are linear and isotropic, which is often the case. Only the value of the permittivity constant, epsilon, has to be varied. Some classes of media are not linear and not isotropic. In that case, the permittivity constant is replaced by a space-dependent tensor. Such cases are not considered here. The situation becomes interesting at the boundaries between two different media. Changes that occur to the electric field at such boundaries can be addressed by formulating boundary conditions. For example, the capacitor can be understood in this way. An interesting concept that also relates to this discussion is referred to as image charges. Here, a situation with a particular boundary condition is replaced with a completely different situation, so that the boundary condition can be avoided. The example shown at the bottom right is that of a positive charge in front of a flat conducting surface. Replacing that conductive surface with a negative point charge directly opposite at twice the distance creates the same electric field, and the standard problem of electrostatic, namely determining this field, can be solved in a straightforward way. Every electrostatic medium, every electrostatic material can be characterized by its constitutive parameter, the permittivity constant epsilon. Epsilon is the product of the permittivity constant of free space times the relative permittivity epsilon r. Vacuum has a relative permittivity of 1, and the permittivity of air comes very close to that value, with epsilon r equaling 1.0006. Conductors approximately have a permittivity of epsilon r equals 1, and other materials typically have epsilon r values that are significantly larger than 1. For example, glass has a range of values between 4.5 and 10 for epsilon r. Electrostatic media can be furthermore grouped into two classes according to their conductivity. Conductors have close to infinite conductivity, so that free charges can move freely until the field in the conductor is zero. In contrast, dielectrics, insulators, semiconductors, have no free charges, and the conductivity of those materials tends to zero. However, in dielectrics, bound charges associated with atoms and molecules can be polarized by external fields. The polarization effect is illustrated by these cartoons. An external electric field E pushes bound positive charges in the direction of the field. The atoms shown here on the right become slightly positively charged on their right-hand side and slightly negatively charged on their left-hand side. Consequently, the right surface of this cube is now slightly positively charged, whereas the left surface of the cube is slightly negatively charged. Associated with this charge separation is therefore a polarization field that opposes the electric field. This polarization field P is given by epsilon, the actual permittivity inside the cube, minus epsilon naught, the permittivity of free space, times the electric field inside the cube. So P equals epsilon minus epsilon naught times E. The electric flux density D inside the material is given by the familiar equation D equals epsilon E, as long as the material is isotropic and linear. It is important to distinguish between the polarization vector P, which always points in the direction of the electric field E, because epsilon tends to be larger than epsilon naught, and the actual polarization field which opposes the direction of the electric field E. Polarization vector P and polarization field EP are antiparallel. The polarization effect is illustrated here microscopically for a single atom. As soon as the electric field E is applied, pointing to the left, the negative electron clouds tend to the right, so that a charge separation of bound charges occurs. However, since these charges are still bound to the atom, they cannot move away, and no motion of charges occurs outside atoms or molecules. The result is a microscopic dipole that aligns itself with the external electric field E. The polarization effect is illustrated here once more, emphasizing that now quite a number of vector fields have to be considered. Externally, there is an electric field strength Ex, and associated with that an electric flux density D external. Internally, both electric field strength and electric flux density can be different compared to the outside. The alignment of the microscopic dipoles creates a polarization field that opposes the electric field strength E. This is shown in the blue box. The polarization field is equal to minus polarization vector divided by epsilon naught, and because it is antiparallel to the electric field strength, the net electric field strength inside the material is smaller than the external electric field strength. This does not directly affect the internal electric flux density because the permittivity constant inside the material is different from the outside. However, in general, the internal electric flux density can also be different from the external electric flux density because of surface charges. One has to distinguish the bound surface charges that are created by the polarization and that are shown here, and any free surface charges that are placed there. Furthermore, the geometry of the dielectric affects the direction and magnitude of the electric field inside. It might not be immediately clear why the polarization creates surface charges. That's illustrated here. One might think of a chain of negative, positive, negative, positive, negative, positive dipoles. It starts at the point where the electric field enters the dielectric with a negative charge and finishes with a positive charge on the other side of the dielectric. The charges on the inside compensate each other to zero. However, remaining are negative charges on the left-hand side of the dielectric and positive charges on the right-hand surface of the dielectric. Since the polarization field EP is antiparallel to both field and polarization vector P, it is given by minus P on epsilon naught. Therefore, the electric field strength inside the dielectric is weaker due to this polarization field. Formally, the electric flux density is given by the sum of epsilon naught E plus the polarization vector. For an infinite dielectric with no free surface charges, the electric flux density is therefore unchanged inside. However, if the geometry is complicated and a finite dielectric is considered, the electric flux can be larger because field lines are drawn into this dielectric. This is a simulation of the polarization effect for a finite dielectric. On the left-hand side, the electric field is shown, and it is clear from the blue color that it is weakened in magnitude due to the opposing polarization. The high permittivity of the oddly shaped object pulls in field lines. This is the reason why the D field, the electric flux density, is strengthened inside the object. This is shown by the simulation on the right, where red indicates that the electric flux density is particularly strong in regions where the surface of the object is almost parallel to the electric field. For linear and isotropic media, the relationship between electric flux density and electric field strength is fully described by the constitutive relationship D equals epsilon naught times E plus polarization vector, which can be manipulated to read D equals epsilon R epsilon naught times electric field strength, which equals epsilon times electric field strength. Here epsilon R is the relative permittivity with a dimension of unity. Epsilon naught is the permittivity of free space measured in farad per meter. Epsilon is the permittivity of the medium, also measured in farad per meter. Epsilon naught has the value of 8.85 times 10 to the minus 12 farad per meter. The question arises what happens at boundaries between dielectrics. Such a situation is shown here. Dielectric 1 interfaces dielectric 2. An external electric field E penetrates both dielectric media. Assuming that the relative permittivity epsilon R of dielectric 1 is different from that for dielectric 2, the surface charges on either side are different. Furthermore, due to the different polarization field, the electric fields inside each dielectric are also different. If a boundary is accessible, it is furthermore possible to add free surface charges to it, so that the surface charge density is changed once more. This is exactly the situation that was discussed at the beginning of this video, namely that of a MOSFET transistor, where a conducting gate electrode, for example gold or aluminium, interfaces silicon oxide, an insulator, which in turn interfaces the semiconductor silicon. The voltage and charge that is placed on the gate electrode is typically well known. How can the standard problem of electrostatics, namely the determination of the electric field strength E in the insulator and then also in the semiconductor, be solved? Since the Maxwell equations are of general validity, they are again the starting point. The second Maxwell equation of electrostatics reads: curl of E is equal to 0 everywhere. Using Stokes' theorem, this can be changed into an integral equation, which says that the closed path integral over E dl is always 0. We can therefore construct a suitable closed path across the boundary and apply this Maxwell equation. It is important to recognize that on either side of the boundary, the electric field strength is different. As usual, it can be split into a component that is normal to the boundary, En, and a component that is tangential on the boundary, Et, tangential. The same is true for the other medium, medium 2. Again, the electric field strength E can be split into a normal and into a tangential component. The path we may choose is a rectangle with two sides effectively parallel to the boundary and the two other sides perpendicular to it. Going from A to B and also from C to D, the path is therefore parallel to the tangential component of the electric field strength. The other two sections of the path, from B to C and then from D to A, are, however, parallel to the normal component of the electric field strength. All four sections contribute to the closed path integral E dl. However, we can make the contributions of the sections BC and dA insignificant by making these sections as short as possible, so that they only just start on one side and barely stretch into the other side. This can be achieved by defining intervals h on 2 that we let to tend to 0. The closed path integral is then effectively determined by the two sections that are parallel to the boundary. Here the approach is shown in detail. The electric field strength on either side of the boundary is split into a normal and a tangential component. This is possible because of the principle of linear superposition. Then we write down the Maxwell postulate in general in integral form, namely that the closed path integral over E dl has to be equal to 0 everywhere. After defining a rectangular path, we can then identify four contributions: sections A to B, B to C, C to D, and finally D to A. By reducing the delta H, we can make the contributions to this path integral smaller and smaller that are due to sections B to C and D to A. They therefore tend to 0. This means only two terms will remain in the closed path integral, and their sum is required to be 0 because of the Maxwell postulate. In each of these two integral contributions, there is a scalar dot product. If we now split the electric field E2 and then also E1 into its tangential and normal components, the normal component, because it is perpendicular to the path differential, will give a 0 contribution to the integral. In contrast, the dot product of the tangential component and the path differential will give a non-zero value. We are at liberty to make the sections A to B and then C to D as short as possible without any restrictions of generality. Defining these sections as delta L and making delta L smaller and smaller, but not 0, we then obtain the equation 0 has to be equal to the tangential component of electric field 2 times delta L minus tangential component of electric field E1 times delta L. The minus sign comes about because the tangential component of E1 and the differential length element delta L are antiparallel. Rearranging and cancelling of delta L gives the very important boundary condition E2 tangential is equal to E1 tangential. In other words, the tangential component of the electric field vector is unchanged at any boundary between dielectric media. Let us now exploit the other Maxwell equation of electrostatics, divergence of D equals the charge density of the free charges, in a similar fashion. Applying the divergence theorem, we obtain the integral version as the closed surface integration d ds is equal to the charge q enclosed. Instead of now designing a closed path about the boundary, we instead designing a closed virtual Gaussian surface. This may be the cylinder that is shown in the diagram. Assuming, as is generally the case, that the two dielectrics don't have any free charges inside, the only free charges inside the virtual Gaussian cylinder are those right at the boundary, given by the surface charge density ρs. And using a similar argumentation, namely by compressing the virtual Gaussian cylinder, one can also show a boundary condition for the normal component of the electric field, specifically for the electric flux density. This boundary condition is that the difference between the normal components of the electric flux density in medium 1 and medium 2 has to equal the charge density of the free charges on the boundary, ρs. Consequently, when the field is known in one of the two dielectrics and the surface charge density at the boundary is also known, the electric field in the other dielectric can be determined in magnitude and direction using the two boundary conditions, and the standard problem is solved. The two boundary conditions can be readily applied to the important boundary between a conductor and an insulator, a dielectric. The dielectric may be medium 1, whereas the conductor is labeled 2. Two important technological examples of the dielectric conductor boundary are the coaxial cable and the capacitor. In a coaxial cable, the lead is surrounded by an insulator, which again is surrounded by a conducting shield, which then is again surrounded by an insulator. Therefore, in a coaxial cable, there are three conductor-insulator boundaries. In a parallel plate capacitor with a dielectric filling, there is a conductor dielectric boundary on one plate and a second such boundary on the other plate. Let us apply the two boundary conditions. E1 tangential equals E2 tangential, and D1 normal minus D2 normal equals the density of the free charges at the boundary. A conductor is by definition free of electric fields. Therefore D2 normal equals 0, also E2 tangential equals 0. We can conclude that D1 normal has to be equal to the density of free charges ρs, and E1 tangential equals 0. In other words, the electric field lines at a conductor surface are always perpendicular to this surface. There is no tangential component. Furthermore, the magnitude of the field near the conductor surface is given by the free surface charge. A closed conducting surface has therefore no field inside, since D2 normal equals 0 and also E2 tangential equals 0, everywhere on that surface, which is the explanation of the Faraday cage effect. Let us now apply the two boundary conditions in a capacitor. Here, a dielectric with a permittivity of epsilon is inserted between two conductors. This is most generally illustrated at the bottom left. Conductor 1 is carrying positive charges that create an electric field in the dielectric that extends to conductor 2, which carries negative charges. Since there is an electric field between conductor 1 and 2, there has to be a potential difference V between the two. If we consider the total charge Q on one of the conductors, then that is given by the surface integral over the surface charge density. This is a surface integration because inside the conductor there are no free charges. Since the first Maxwell equation, Gauss's law, is always valid, we can set this equal to the surface integration of epsilon E field times ds. between E and ds is a scalar dot product. If we now apply the boundary condition between conductor and dielectric, we know that there is no tangential component of the electric field. Therefore, this surface integral becomes E normal epsilon ds. The potential difference V along any one of the field lines between conductor 1 and conductor 2 is given by V equals minus the path integral from 2 to 1 E times dl. Defining the capacitance of the capacitor as usual as the ratio of charge carried by the potential between the plates, we can derive an equation that determines the capacity as the function of the geometric parameters. We simply replace Q with the relationship we obtained on the slide before, namely surface integration of epsilon E times ds, which we know is equal to epsilon times the normal component of the electric field strength times ds, and divided by the equation at the top, namely minus path integration from 2 to 1 over E times dl. Considering now the specific case of a parallel plate capacitor, the numerator becomes epsilon EA and the denominator becomes E times D. Cancelling the electric field strength E, we obtain the familiar equation for the capacitance that only depends on permittivity of the filling epsilon, the area A of the plates, divided by the distance of the plates D. And it is measured in farads, whereby the minus sign is usually ignored. Concluding this discussion of electric fields in materials and at boundaries, let us briefly touch the method of image charges. We have already established that right at the boundary of a conductor, the electric field vectors are perpendicular to the surface of the conductor. However, what does that field look like in the vicinity of it? How does it change as we go away from the conductor? The simplest case of this is a point charge in front of a conducting surface. What does that field look like? This is not readily calculated for the situation illustrated because the field has an interesting shape and then finishes abruptly. The field can, however, be calculated in all regions by taking a lead from optics, where an object is mirrored by an image. How can we mirror the electric field of a point charge in front of a conducting surface? This is possible by removing the conductor altogether and placing a negative point charge at twice the distance. We have now reduced the complex problem of the field in front of the conductor to the much simpler field of 2 point charges, a positive and a negative point charge. In fact, it is the field of an electric dipole. We have thus solved the standard problem of electrostatics simply by replacing the boundary.